Hi students, welcome back. So today we will continue current electricity. The topic which we are going to study today is effect of temperature. Effect of temperature on resistance or resistivity. Okay. We have studied about resistance rho L by A, specifically what is resistivity, into it deep physical level, like into the material. To the particle level we have seen like how charges, how electrons, its mass will affect resistance. So we'll start from there this topic also. Okay, so R is equal to rho L by A, and expanding this rho from the basic derivation we have done in the last classes, we can write R is equal to ML by resistance is ML by N E square tau into A. So from this we can write rho is M by N E square tau, where this rho is resistivity, M is nothing but mass of electron, N is what? Volume density, or we can say number of electrons per unit volume. That is what is N is, that is number density. Then this is E is charge of electron, and tau is what? Tau is average relaxation time. Say for example here one kernel or ion is there, electron is coming, colliding with this. After colliding, it will be going in another direction, it will be colliding with another, then again it will go and collide. So this is called relaxation time. So time between two collision is what is relaxation time, or we can say that time gap with which electron relaxes a bit, remaining all the times it keeps on doing collision, full fight. So when we consider the whole relaxation time of all the electrons, we take the average. We have seen all that derivations. That is what is average relaxation time. Clear? Average. So this is the expansion of this formula. Okay, just a quick recap I have done just for getting a better idea. Okay, so R is equal to rho L by A, ML by N E square tau into A. Okay, so R is equal to rho L by A, or ML by N E square tau into A. Okay, or rho is equal to M by N E square tau. Now how temperature will affect this, we'll see. Suppose if we increase the temperature, consider this formula, directly we can understand what will happen to mass of electron if we increase the temperature. It will increase or decrease, or it will be constant. Mass will be constant. Mass will change only if the particle travels with such high velocity, then mass will change. Remaining all the time, mass will be constant. So this is constant. Now if temperature increases, what will happen to this charge? This is also constant. Charge of an electron will never change by changing the temperature. What about N? Number of free electrons. Number of free electrons per unit volume. What will happen to that? This will increase. This will increase because of more ionization energy. If we increase the temperature, electrons will be inside atoms. But if we apply heat, temperature will increase and these electrons will get energy, ionization energy we say, it will come out of the atom. So number of electrons will increase. Okay, so that is that one. Remaining all the things are constant. Now what about relaxation time? When temperature increases, what will happen to relaxation time? This relaxation time will decrease. Why? Because when we increase the temperature, vibration and movement of these particles will increase. So more collision, more movement. So the time between two collisions will decrease. Okay, so previously after colliding with another particle, it will become and collide with another particle. But now what will happen? Tuck tuck. It will be very fast. So the time gap, average relaxation time will come down. Clear or what? So when you increase the temperature, number of electrons will increase, the average relaxation time will decrease. Now what about length and area? Length and area also will change, because in thermal properties of matter, first year topic, we study this. When you increase the temperature, length will increase, area will increase. But here we are neglecting it, because the change in length, change in area is very small and it doesn't affect overall resistance, because that increase or decrease is very too small, so that it will not change resistance at all. It will not make any effect, so we are neglecting it. So all these we consider as constant. Only number of electrons, relaxation time. Now if what will happen if temperature increases, N increases, N is in denominator, what will happen to resistance? Resistance will decrease. Now this one, if relaxation time, if this decreases, what will happen to resistance? Resistance increases. Or we can say resistivity decreases, resistivity increase here, so resistance increase, resistance decrease. Now here there is a fight between these two things. So which one will dominate? Here this will dominate. This will dominate. Why? Because already there are around 10 raised to 29 free electrons in a unit volume, or we can say cubic meter. Unit volume, that is 1 meter cube volume, 10 raised to 29 free electrons are there. Okay, so in metals or in conductors, already the number of free electrons is too much, too high. There are around 10 raised to 29 free electrons are there in a unit volume. So even if we increase the temperature, the increase in N is very small, very small. But the decrease in relaxation time is much when compared to this. So that is the reason the reduction in relaxation time or the decrease in relaxation time dominates the increase in the number of free electrons. Already conductor is full of free electrons, lot of free electrons are there. So no much difference is going to happen here. The difference will be there, but very minute. This dominates. So overall from here we can understand, when temperature increases, resistivity increases, resistance increases in conductor. So specifically we are studying about conductor in this chapter, resistance and all we study about conductor. So temperature increases, resistivity increases, resistance increases in conductor. So conductor, then semiconductor and some alloys. These are the things generally we study in physics regarding resistance, current, or this area, circuit related things. These three we concentrate in the sense we have these three involvement in the topic. So conductor is clear. When you increase the temperature, resistance will increase. Now we will see what will happen to semiconductor. In the case of semiconductor, again N and tau. So temperature increases, same way N increases, rho increases, R increases. Then temperature increases, what will happen to tau? Tau decreases, rho decreases, resistance decreases. Now between them how the trade-off will happen? In the case of conductor, we said like 10 raised to around 28, 10 raised to 29 free electrons are there, but that is not the case with the semiconductor. Semiconductor number of free electrons are less compared to conductor. Insulator, it is completely null or very few, but better than insulator. Semiconductor, some free electrons will be there, but not like metals or conductor. So here what happens is the increase in N dominates the decrease in average relaxation time. So what happens? This increase, okay, dominates, okay, the decrease in relaxation time. So what will happen overall, since this is dominating, what we are getting? Resistivity decreases, resistance decrease. So in conductor, when we increase the temperature, resistivity increases, resistance increases. But in semiconductor, as we increase the temperature, resistivity decreases and resistance decreases. The reason already we discussed. Okay, note it down. What about alloys? Why we use alloys here? See, suppose if you have a manufacturing unit of resistors in, for example, Chennai. So there the temperature is temperature range we know. If we are manufacturing in summer, suppose if the temperature is somewhere around 47 degrees Celsius, and we are exporting this resistors or resistances to some European country or a country where in winter or in some season they get the temperature minus 5 degrees Celsius, minus 6 or minus 8 degrees Celsius. Or for some experiment we are taking resistors, we are doing some experiment in such an ambience that the temperature of the ambience will be minus 10 degrees Celsius. So such a difference is there. If the value of resistance changes, it will affect the circuit and the overall gadget or the experiment will fail. So we cannot accept such change in resistance, okay, or the temperature dependency we need to reduce. So what we do, we make alloys with such materials like it will be a mix of conductor and semiconductor, or it will use such material like temperature will not be affecting the resistance. So this will be in alloys, okay, change in resistance due to temperature will be what? Almost, just we can say almost, just almost equal to 0, not 0 but almost equal to 0. That is the idea. Okay, now we will move into equations and other parts. Okay, so it is like the final resistance is equal to R naught is nothing but initial resistance into 1 plus alpha T final minus T initial. This is the formula, but we will see how this comes, so that some difficulty, or if they play with the question also, you will be able to answer. So how it comes, we will see. So the change in resistance, say for example change in resistance dr, change in resistance, this is directly proportional to initial resistance. Initially the resistance will have a value, right? So after increasing the temperature, that will change, initial resistance will change, but this change in resistance depends on the initial value. If the initial value is more, change will be more. This is number one. Another is this change in resistance is directly proportional to change in temperature. If the change in temperature is more, there will be more change in the resistance. So dr is proportional to dt. Okay, so dr is equal to alpha R naught dt. So this alpha is the proportionality constant. We call them temperature coefficient of resistance. Temperature coefficient of resistance. Okay, now if we make a small change in temperature, there will be a small change in resistance. Again, if we make small change in temperature, there will be small change in resistance. Say for example, if initial resistance was R naught and final resistance becomes RF, when we change the temperature from initial temperature to final temperature, say for example initially the resistance was R naught, now we changed that resistance to RF by increasing the temperature from Ti to Tf. So all those changes we will have to add, all those small changes we will have to add. So what we do, this formula we will integrate dr from R naught to RF is equal to integral R naught alpha dt, from where to where? From initial temperature to final temperature. Clear? Copy this. Okay, so this side R integrating R0 to RF is equal to integrating. If we now see, I would like to say something here. Integral R0 to RF dr is equal to integral Ti to Tf R0 alpha dt. Remember this also. It's easy to remember. First thing is, change in resistance is directly proportional to R0. Change in resistance is directly proportional to change in temperature. So then if we are putting the proportionality constant, integrating both the sides. Remember this. So integral R0 to RF dr, integral Ti to Tf R0 alpha dt. Suppose in 99% of the cases, 99% of the cases, this alpha will be constant. Alpha will be constant. Suppose if they give alpha as a function of time, actually alpha will change. Actually this coefficient of resistance, temperature coefficient of resistance will change with the temperature in practical scenarios. But we get questions as alpha is constant. Suppose if they give a question where alpha is a function of temperature like T square plus T, something like that, then we will have to put that equation here and we will have to integrate and get the answer. So formula in this form is also important. Now what we will do, we will consider alpha as constant and we will proceed further. So here integrating this, what we get RF minus R0 is equal to R0 alpha T. Putting the limits, what we get Tf minus Ti. Clear? So here RF is equal to, this will go to this side, R0 plus R0 alpha delta T. Tf minus T0, we will take delta T. So RF is equal to R0 in R0, if we take outside, this is going to be 1 plus alpha delta T. So this is the formula concerned with the temperature dependency of resistance. Okay, final resistance, initial resistance, temperature coefficient, and this is Tf minus T0. Whatever be the change in temperature, we can put there. Okay, pause the screen and note it down. So here this one we can extend the formula. Resistivity itself is changing. So final resistivity L by A. This is what is RF. Same way rho naught L by A into 1 plus alpha delta T. So A, L, L, everything will be cancelled. So final resistivity is equal to initial resistivity into 1 plus alpha delta T. So this also can be used here. Then alpha, the formula for alpha. So that also, suppose if RF is equal to R0 into 1 plus alpha delta T. So from this formula we can derive alpha also. So alpha directly I am writing Rf minus R0 divided by R0 delta T. Remember this also. Without wasting much time, we will be able to get many answers from that relation also. So what will be the unit of alpha? Unit of alpha. This is also resistance, this is also resistance. So ohm unit will get cancelled off. So unit of alpha is going to be Kelvin raised to -1 or degree Celsius raised to -1. Kelvin raised to -1 is the SI unit. So for conductor, this temperature increasing with the resistance increasing with the temperature, resistance decreases with the temperature, all these factors will come here with alpha. So for conductor, alpha will be positive. For semiconductor, alpha will be negative. And for alloys like nichrome and all, alpha will be not actually 0 but almost equal to 0. Slight variation will be there, but it is almost equal to 0. We will do some questions on this. Okay, we'll do this question. The resistance of a heating element at a room temperature 27 degrees Celsius is 100 ohm. At what temperature its resistance will be 117 ohm if alpha is 1.7 10 raised to -4 degrees Celsius raised to -1. So options are given here in degree Celsius. So we need to find the temperature at which the resistance reaches here. So by Rf is equal to R0 into 1 plus alpha delta T, that is the formula. But directly we can do, if we use this formula, that will be better, like Rf minus R0 divided by R0 into delta T. So in delta T we can substitute this Tf minus Ti. Tf minus Ti. So from here it will be better, easy. So this is Tf minus Ti. So Tf minus Ti is equal to, this will come this side, Rf minus R0 divided by R0 into alpha. So Tf is equal to, Ti will go to that side, we'll add it. So what is the final resistance? 117. R0 is 100 divided by R0 is again 100 into 1.7 into 10 raised to -4. Ti is how much initial? Yes, 27. We'll just add it off. So here 17 will come. So here also the 17 we can adjust. So answer will come as how much? This is 17 divided by 1.7 into 10 raised to -2. Okay, so plus 27. So if we, this will become 10 raised to -2 will go up, so this will become 10 raised to 3. So totally how much? 1027 degree Celsius will be the answer, option D. So 1027. So this is the next question. Okay, the resistance of a platinum wire is 5 ohm at a ice point and 5.5 ohm at a steam point. Find the resistance at which find the temperature at which resistance of the wire is 5.8 ohm. So first thing which we need to understand is ice point is nothing but 0 degree Celsius and steam point is actually 100 degree Celsius. Okay, so the resistance of platinum wire is at 0 degree Celsius, the resistance is 5 ohm, and at 100 degree Celsius resistance is 5.5 ohm. So at what temperature, at T degree Celsius, this is going to be 5.8 ohm. So that is what. So how to find out? So copied the data, I am erasing this. Options we will write here. Okay, 120, 160, 200 and 240. Okay, so RF is equal to R0 into 1 plus alpha delta T. Another thing is alpha is equal to RF minus R0 divided by R0 delta T. So this is same wire or different wire? All these are same wire, all are platinum, right? Platinum wire. So alpha is going to be constant. So what we will do? We will equate the alpha also, we can find out. So let's write one by one. So first thing is 5.5 is the final resistance for this one, is equal to 5, okay, to steam point, to 1 plus alpha delta T. So alpha into 100 minus 0, so we will write like this. Now then what about this? 5.8 is equal to 5 is the initial resistance into 1 plus alpha into T. This is what. Now here by using this formula we will equate. Alpha is same. So what about here? 5.5 minus 5 divided by 5 into 100 in this case is equal to what? Like in this case we will take 5.8 minus 5 divided by beginning initial resistance is 5 into delta T is T minus 0, that we will write like this. So from here easily we can find out, many calculations can be avoided. So this is nothing but 0.5 divided by 100 is equal to, here what is this, 0.8 divided by T. So what will be T? T will be 0.8 divided by 0.5 into 100. What will be the option? Correct option. How much? 160. If you solve this, you will get 160 degrees Celsius. So you can use direct method also, but if you remember that formula and if you apply that wisely, much of the calculations can be avoided. You can save. This is a classic question which has real link with the practical scenario. See, two actually they have connected. This is a single resistor, but two materials are connected like this. The length and area of cross section of both the materials are same. area of cross section, length L is also given. But this metal's resistivity and temperature coefficient is ρ1 and α1. Its resistivity is ρ2 and temperature coefficient is α2. Find the relation between ρ1 α1 ρ2 α2 such that the resistance of the combination is independent of the temperature. And the relations are also given. Very good question. So I request you all to pause the screen and think for some time. Try to answer yourself. If you do, if you think, if you do slowly by on your own, your capacity will increase. Okay. So try, take some time, 5 to 10 minutes, no problem. Take as much time as you want, but try to solve this. So I just erase the question. So one method to solve this question is, see, Rf is equal to R0 into 1 plus alpha delta T. So actually what is the change in resistance? Rf is equal to R0 into, if we multiply it inside, plus R0 alpha delta T. So Rf minus R0 is equal to R0 alpha delta T. So this is the change in resistance. Now the crux here is, the point here is, if we need to avoid, if we need to take that temperature dependency, then one of the alpha must be positive and another must be negative. Okay, so if we increase the temperature, the resistance of this piece will increase, the resistance of this piece may decrease, or either way. If we do that, the overall resistance will be constant even if we change the temperature also. That is the idea. So what we do is, one piece will have increase in the resistance and another piece will have decrease in the resistance. So if I take, if I consider this as 1 and if I consider this as 2, then Rf minus R0, actually if we take this R0 into alpha 1 into delta T plus R0 of that one plus alpha 2 into delta T will be 0. The sum of change in resistance of that must be 0. One will be plus, the other will be minus. So best thing is what? R0 1 into alpha 1 into delta T. Change in temperature for both are same. We are applying, both are together, right? So change in temperature for both of them are same, is equal to R0 2 into alpha 2 into delta T. Did you understand how I wrote this? The change in temperature, the change in resistance of this and change in resistance of this, putting together, the addition of change in resistance of these should give 0. The intention is resistance should not change with the change in temperature. So if we add these both, the change in resistance of this plus change in resistance of this, if we add, we should get 0. That is, one will be plus and another will be negative, then only that will happen. So we can write like this, no? One, this plus this is equal to 0 means this must be equal to this. Clear? So here ρ1 L by A alpha 1 delta T is equal to ρ2 L by A alpha 2 delta T. So cancel all the similar terms, AA, LL, alpha T, alpha T. So ρ1 alpha 1 minus ρ2 alpha 2 is equal to 0. Rho 1 alpha 1 minus rho 2 alpha 2. Option B is correct. Pause the screen. Copy this. Another method is there, that also I'll write, but this is easy. I feel like this is easy. Some of you might have done in that method also. See, if this is R1 and if this is R2, so this is like a series, right? So R1 plus R2, this is its normal resistance before changing the temperature. Now if we change the temperature, what will happen? This R1 will become R0 into 1 plus alpha delta T, plus again this will change R0 into 1 plus alpha delta T. This is alpha 1, this is alpha 2. Clear or what? So this was the initial resistance, this was the initial resistance. So we can put here R1 and this is R2. Nothing wrong in that. Okay, this is how it is going to be. So now we will replace with the resistivity. So rho 1 L by A plus rho 2 L by A is equal to, put it inside or no problem, rho 1 L by A into 1 plus alpha 1 delta T plus rho 2 L by A into 1 plus alpha 2 delta T likewise. So here this, if we multiply inside this thing, this term will come this side. So anyway, L, L, A, L, L, all this can be cancelled off. Okay, so rho 1 plus rho 2 is equal to, multiply it inside, rho 1 plus rho 1 alpha 1 delta T plus rho 2 plus rho 2 alpha 2 delta T. So rho 1 comes this side, this will be cancelled off, right? Rho 2 will be cancelled off. So what will happen? This will come to this side, rho 1 alpha 1 delta T minus is equal to rho 2 alpha 2 delta T. This is how. Now this delta T will be cancelled off. So what is the answer? This will go to that side. This is equal to 0. Rho 1 alpha 1 plus rho 2 alpha. Okay, so understood, right? In this formula we replace it with the rho L by A. All L, L, A, everything cancelled off. This rho 1 is multiplied inside. So rho 1 plus rho 1 alpha 1 delta T, likewise we get rho 1, rho 2 will get cancelled off. So when we bring one term to this side, delta T also will be cancelled off. So again we will get rho 1 alpha 1 plus rho 2 alpha 2, same relation we get. So this is a very good question. Do it, practice it. If you did not get yourself, go through the solution, practice it. Okay, so effect of temperature on resistance, that topic is done. Revise it today itself, go through your notes today itself, complete your notes, then try to solve some extra questions from previous years, JEE, Neet, APMT, all that. Okay, students, bye bye, good luck, study well, thank you so much.